Hi, welcome back to RISC-V CPU design. So far we have built the datapath and the associated control that supports R-type, I-type, S-type, and B-type instructions. In that process we have added pretty much all of the hardware that we need to support all of the remaining instructions in the instruction set. The changes that we need to make to support the remaining instructions are relatively small. So let's see what do we need to add to support JALR instruction. That's the instruction that stands for Jump and Link Register, which is the one that we frequently use for function calls. So JALR is an instruction of an I format. That's the same format as we have used for arithmetic with immediates and for loads. In that format, we have an immediate in the upper 12 bits and then fields for one source register and one destination register. So the format of the instruction is JALR RD RS immediate. The instruction does two changes to the state. It writes PC plus 4 to a destination register, which we'll be using as the return address from our function call, and then jumps to the function by writing the RS1 value plus the immediate to the program counter. Notice that the use of the immediate format for JALR presented a compromise. We lost one bit of a range because always the last bit of the immediate is set to 0, so we lose one bit of how far we can go with a JALR, but it simplified the data path. We are essentially reusing the immediate generation mechanism from the I-types. So here is the data path that we have built so far. It has the instruction, the program counter, the instruction memory, the register file, a branch comparator that we don't need this time, the ALU, the data memory, which we don't need either, and the control. We need to do two things. First, we need to figure out how to write the value of PC plus 4 into the destination register in the register file. And there is no immediate path. We'll need to somehow add a multiplexer for that to happen. Then for the second part, where we are going to be adding RS1 with an immediate, we already have the mechanism. We'll be using the ALU, and we are going to write it through the same hardware that we have used for supporting taken branches. So here is what is the modification that is needed to support JALR. It is just adding this path that enables us to write PC plus 4 to a destination register. We have done that by widening the write back select multiplexer to have three possible inputs. One where the write back value may be coming from the destination memory, one where the write back would be coming from the ALU, and the third one is the PC plus 4 value. We could have done this differently. We could have added one more multiplexer in series and another control signal, but this way is simpler. We just widen the multiplexer and we are using a 3-position switch here for write back select. So write back select has 3 different values, 0, 1, and 2. The rest of the modification is simply done through the control. So there are no modifications to the data path. We just have to set the control bits the right way. Notable thing here is PC cell control signal is always set to taken, which means we are behaving like we are always taking a branch, because it is a jump. Immediate select is of I-type because we are sharing the format with I-types. We do enable writing to the register file because we do have to write the destination value to the destination. We need to write the return address to the destination register. We ignore everything that is associated with the branches. We set the AB multiplexers appropriately, and ALU is set for an addition. We are not working with the memory, so we set it to read, which is the default state, and write back select is 2, as we already mentioned. Let's light up the JALR datapath. We start with fetching the instruction and we can immediately proceed to the decode. One notable thing here is we, instead of lighting up this path of PC+4 value going back to the input of the program counter, it does happen, but this is a path that is never going to be taken, so we are just lighting up the path that takes it to the write back select. After the control logic sets all these signals appropriately, we can proceed with the rest. So actually concurrently with setting up the control registers, immediate generation is going to happen and RS1 value is going to be sent over to the ALU. RS2 is being ignored because it is invalid. We don't have RS2 in the field, in the instruction field. The output of an ALU will be the sum of the RS1 value with the immediate, and that is going to be sent back to the PC cell multiplexer. That one is set always to take that value, not the PC+4. That's going to be put at the input of the program counter. So that is going to happen simultaneously with the write back select multiplexer presenting the PC+4 at the input of the RD. On the next clock tick, those two states are going to be updated. And that's it. We'll see some other instructions after we come back.